Good afternoon, guys. I hope you can hear me. So we are now continuing with what was discussed in the last class. We are talking about a capacitor and seeing how capacitors can store energy. Okay, and if you remember what you have studied in chapter number 28, you know that work done in arranging charges in a certain configuration is equal to the change in potential energy. Or in other words, if an external agent can do work and then separate positive and negative charges and put them in a certain configuration, then the potential energy of the system is increasing. And you know that potential energy is stored energy. And then when these charges which are there on the opposite plates are able to come together again, then the energy is released. And this process is called discharge. Okay. Now let's actually arrive at the equation for the energy stored. So what we'll do here is we will first of all consider the two plates, the two parallel plates, and let's say at a time t equal to 0. At a time t equal to 0, the charges are 0. Q equal to 0 minus Q equal to 0, and potential energy is also, the change in potential is also 0. Potential difference is also 0. And then you start the process. You now connect a battery. You start the process of charging. Okay, after you start the process of charging, let us see what is the picture after some time t. Okay, so now let us look at the picture at some time t. So at a time t, what happens is you're finding that the charge is no longer 0. The charge will be equal to, on the plates will be equal to some q prime and minus q prime. Q prime and minus q prime will be the charge on the two plates. And then you know that if there is a positive charge and a negative charge separated by a distance, there is going to be an electric field. Okay, or there is going to be a potential difference. So let delta V prime be the potential difference when the charge on the plates be Q prime. Okay, now you know that capacitance is a constant. It doesn't change or depend on the charging. Therefore, you can write an equation connecting all this. You will write Q prime equal to C into delta V prime. Or if I want the expression for the potential difference is Q prime divided by C. Okay, this is at a time t, at t equal to t. Okay, now what we'll do is, let us look at the picture at a time t plus dt. At a time t plus dt. Charging is still going on. Remember, charging is still going on. So what happens is, at a time t plus dt, the charge on the plates would have increased a little more. Let the charge increase be q prime plus dq prime, and similarly here it is minus q prime minus dq prime. Okay, let me again repeat to you. When the time is 0, the potential difference was 0, the charge is 0. At a time t equal to t, let the charges be q prime and minus q prime. And then you know that if it is q prime and minus q prime, you know that, I'll write it so that it is clearer. It is minus q prime at a time t equal to t, and then at a time t plus dt, some more charge would have gone on the plate. So let the charge be q prime plus dq prime, and here it is minus q prime minus dq prime. So as a result, what happens? The potential is not going to be dv prime. Now the potential is going to be changing. Okay, so let us now write the expression for what is going to be the increase in the potential energy in this time duration dt. In this time duration dt, let the change in energy be, you know that if q prime, dq prime is the charge involved and delta v prime is the potential difference. So the product of these two will be equal to the change in potential energy. So this is the amount of potential energy that increased in this time interval dt. So what you do is du is equal to delta v prime into dq prime. And already you have the expression for delta v prime. It is q prime by c that you get from here. Substitute. Okay. So we are just looking at how much is the energy increase in the small time interval dt when a new amount of charge dq prime got deposited on the plates. Because you know the relationship between potential difference and potential energy difference. So potential energy is given by potential difference into the charge. So that's how you're getting this equation. Now this is for a small time interval dt. But Let us look at the entire charging process. The entire charging process happens between t equal to 0 and some t equal to t, the end of the charging. Okay, so what we will do here is, what is the, if Q is the total energy that is transferred during this total charging period, then let us find out what is the total potential energy stored. For a time dt, you know that potential energy is du. Now for the total time, you just have to do an integration. So how do you do the integration? You have to do the integration from 0 to time t. Or let us write the expression for du. Du is q prime by c into dq prime, which you did in the previous page. And here you can see that q is the function of time. The amount of charge on the plate is changing as a function of time. So it's a function of time. Therefore, at a time t equal to 0, the charge is 0. At a time t equal to the final time, the total charge is q. So you do the integration from 0 to q. When you do this integration, you're seeing that 1 by c becomes a constant. So it comes out. And then you have integral q prime dq, okay, which is simply q prime square by 2. Or you are finally getting the expression for the total potential energy that gets stored because this potential difference was created in a time 0 to t. Okay, now you also can see that this half q square by c can be rewritten as half c delta v square. Okay, this is because we know the relationship between q is equal to c into delta v. Okay, therefore you can see that q square is equal to c square into delta v square. So using that, you can also arrive at this equation. Or in other words, the potential energy of a system is directly related to the charge and the capacitance, or the charge and the potential difference. I'm sorry, the potential energy stored in a capacitor is dependent on the charge and the capacitance value, or you can also say it as charge and the potential difference between the two plates, because potential difference is related to how much charge is there on the plates. What is the unit of energy? Potential energy? Unit is joule. Okay, now the question is, okay, so now you are saying that there is a capacitor. One plate has been charged and made plus Q. The other has been charged and made minus Q. Okay, now where is the energy stored? Where is the energy stored in the capacitor is the next question. That let us try to answer. So what we'll do is, you charge a capacitor and then isolate it. The meaning of isolating is remove it from the circuit. Remove the battery. When you remove the battery, then you have isolated the capacitor. Isolated means it is not in contact with anything else, or the two plates of the capacitor are now not in touch with the rest of the world. Are you able to hear me still?
Yes, ma'am.
Right, because there was a momentary power cut. Okay, so it's come back. I have a backup, but still I just wanted to know. Okay, so what happens here is, the two plates are there, they are charged, and you have removed the battery. So that means these two plates cannot communicate with the external world anymore. Okay, so whatever charge is on them remains. So that's the meaning of an isolated charge conductor, capacitor. So take such a capacitor, let the gap between the plates initially, be D. Okay, let D be the plate gap. Now what you do is, you pull the plates apart. Externally, you put your hand and then pull the plates apart so that this gap is doubled. Okay, what is the formula for the capacitance of a parallel plate capacitor? C is equal to epsilon naught A by D. Okay, now when you double it, what happens to the capacitance value? Denominator becomes 2D. Therefore, what happens to the capacitance value? The capacitance becomes half. The capacitance value becomes half. Okay, and you can see that because it is an isolated capacitor, you just used your hand and pulled it, but then there is no other conductor which is going to take away the charge on the two plates. Therefore, Q on the plates remain. The charge on the plates will remain, it doesn't change. Okay, therefore, you can also talk about what is going to be the new energy on the energy in the capacitor. What will be the new energy in the capacitor? Anyone? Use this. Use this and tell me what will be the new energy. C value has become C prime. C prime is half of C. Half of C. So what will be U? What will be the new value of U? Just look at this equation. Here, Q is the same, but C has become half. Okay, therefore, what will happen to potential energy? The new potential energy will be 2 times the initial potential energy. Is that difficult to understand, guys? First, the plate gap is D. Now you make it 2D. When you make it 2D, what happens is the capacitance becomes half because the formula AC is equal to epsilon naught A by D. D became 2D. Therefore, the new capacitance is half of the original capacitance. Okay, now let us find the energy. Because C has become half of the original value, the potential energy becomes doubled. C is the denominator of that equation. Therefore, energy becomes doubled. Okay, so what you're seeing is when you are using a hand or something and then pulling the plates apart. Please remember these two plates are opposite charge. So therefore, there is an attraction. They want to be together. But then you are pulling it. That means an external agent is going to do work. It's going to do positive work to pull. Okay, in doing that, what has happened? The capacitance value became half and the energy became double. Now let us look at the two plates of the capacitor and see what geometric part of this capacitor doubled when you pull the plates apart. When you pull the plates apart, the volume between the two plates got doubled. The volume between the two plates got doubled. So you can conclude that the energy is stored in the volume between the two plates. The charge did not change. The charge is the same. Plate area did not change. That also remains the same. But energy doubled. Energy doubled, and another factor that doubled was the volume between the plates. Therefore, you come to the conclusion that energy is stored in the space between the two plates of the capacitor. Energy is stored in the space between the plates of the capacitor. And between the two plates of the capacitor, there is something. What is that? That something is electric field. You know that there is a uniform electric field between the two plates. Therefore, you come to the conclusion that in a capacitor that is charged, energy is stored. And where is the energy stored? Energy is stored in the electric field between the plates of the capacitor. It is between the plates of the capacitor. And what is responsible for this electric field? It is the charge. So the charging is crucial. When you charge only, there is energy. Capacitance does not depend on charging and discharging, but energy depends on the charge or how much of charge is there. Now we can talk about how much energy was there in the total volume. But now there is also another number that we can talk about, that is called the energy density. And look at the symbol used, it is italic small u. Italic small u, it is called the energy density. Energy density is energy per unit volume. Energy per unit volume. So energy density can be, energy is capital U divided by, for a parallel plate capacitor, you know the gap is D and the area is A. Therefore, the volume is AD. Okay, so let's just put that. Potential energy divided by AD. Or potential energy is half C delta V square. Okay, therefore you write 1 by 2 AD into C delta V square. C delta V square. Now what we'll do here is, let us just write the expression for C. C is epsilon naught A by D. Okay. Now once you do that, you're going to get 1 by 2 A D square epsilon naught. Then there is an A here which cancel out, and then you have a delta V square. Or this becomes half into epsilon naught into delta V by D whole square. What is delta V by D? Anyone? What is delta V by D? It is electric field. Minus delta V by D is electric field. Therefore, square. So it is E square. Or you're getting the energy density as half epsilon naught E square. or you're finding that energy density is proportional to the square of the electric field. So this also shows you that energy is stored in the electric field. It is stored in the space between the plates. What will be the unit of energy density? Anyone? Unit? What is the unit of energy?
Joule.
Joule. So energy density, it is energy per unit volume. So the unit will be joules
Per meter cube.
cube, joules per meter cube. However, remember current density is not ampere per meter cube. It is ampere per meter square. It is energy. It is the current per unit area of cross section. That difference you should always remember. Okay, and please remember from here itself you are able to see that energy density is a function of electric field. It's a function of electric field. Okay, so this means that if the electric field is the same everywhere, then energy density will be the same at every point. And you know that between the plates of a capacitor, you know that the electric field is uniform. Because the electric field is uniform, you can conveniently say that energy density is the same at every point inside the parallel plate capacitor. Okay? Remember, this expression that we arrived at, we have arrived at it by using a parallel plate capacitor. But then this expression, U is equal to delta, half epsilon naught E square is going to be valid for any geometry of capacitor. It is valid for a spherical capacitor. It is valid for a cylindrical capacitor also. However, in those places, what happens is electric field is going to be a function of distance. Like for example, if I'm going to have a sphere, okay, a sphere. Now you know that the electric field at a point is going to be given by 1 by 4 pi epsilon naught Q by R square. It's a function of R. Similarly, for a cylinder also, the electric field is a function of R. That means that the energy density is also a function of R. But this expression is going to hold good. Because after all, energy density is half epsilon naught E square. Whatever is the value of E at a point, at that point, the energy density is going to be decided by the electric field there. Or in other words, you can also conclude that energy density is something that can have different values at different positions when it comes to spherical and cylindrical capacitor. Okay. Now I've just given you a job. These kind of things can be useful in an examination. I have two identical capacitors of capacitance value C. Okay. And I'm charging them to the same potential difference delta V. Now, one possibility is you can connect them in parallel. Another possibility is you can connect them in series. Now, in which of this combination will the energy stored be a maximum? I have two capacitors, connect them in series or connect them in parallel. In which case is the energy a maximum? Okay, just do this and see. Okay, next. Here, the problems are long. They are taking a long time. So what I've done is if I have to take you through all the problems, then I thought I better work it out and just discuss it in the class. So what we have here is a 3.55 microfarad capacitor C1 is first charged to a potential difference 6.3 volt. You're taking a capacitor, charging it using a battery. Then what you do? Remove the battery, isolate the capacitor, and then connect this capacitor. And please let us say that C0 is the charge on the capacitor after the charging is over. This is C1. Q0 is the charge, and the potential difference that you are getting is going to be V0. Okay, this is the initial condition. Now take that capacitor and connect it to another capacitor C2. C2 is going to have a value 8.92 microfarad. Connect it and then close the key. Close the key. Okay. When you close the key, what do you expect will happen? When you close the key, what do you expect will happen? So there is charge Q0 plus minus on this plate. This is not charged. There is nothing here. So what do you expect will happen when you close the key? Is there a potential difference between these 2 points? This point and this point? Is there a potential difference? Or what is the potential of the plate C2? Is it charged? I said it's not charged. So what will be the potential of that plate?
0.
0. And you know that charges always go from, if there is a potential difference, charges will flow till the same potential is reached. Till the same potential is reached. So the picture is charges will start flowing till both these fellows will arrive at the same potential difference. After that, no flow of charge will be there. Okay, that's besides the point. I'm keeping that away for a later discussion. But before that, what is asked is, what is this common potential? What is this common potential difference that you are arriving at? So after the switch is closed, charge will flow till potential difference becomes, the potential difference between the two will be the same delta V. Okay. So now what is this delta V is the question. This is also at delta V. This potential difference is also going to be delta V. So what is that potential difference delta V? That common potential difference we have to find out. So what we do is, let us go to the initial picture. Initially, when it is standing alone, charge is Q0, C1 is the capacitance, delta V0 is the initial potential difference. Let us just put the value of capacitance and the potential difference and arrive at the initial charge. So you know the total initial charge. So the total initial charge you can get. And then after C1 is connected to C2, I told you that charges will flow from one capacitor to the other. So let the charges be Q1 and Q2. Let the charges be Q1 and Q2. And you know by conservation of charges, Q0 is equal to Q1 plus Q2. Now what you do is, let us write Q0, Q1 and Q2 in terms of capacitor value and delta V. So here the initial potential difference is delta V0. C1 is the capacitance value. And the second, on the right hand side, Q1 can be written as C1 into delta V because delta V is the final potential. Similarly, Q2 can be written as C2 into delta V. Okay, and I've given the reason. That is because charges will flow until the potential difference becomes the same across C1 and C2. Now you can see that delta V is common. Take it out of the bracket. So you can finally have delta V on one side and get everything else on the right side and substitute. You will get that common potential difference as 1.79 volts. Guys, I again tell you, when you are going to connect a fully charged capacitor C1 to another capacitor C2 and then close the circuit, there is a potential difference between this plate and this plate. So charges will start flowing. Similarly, from this plate to this plate, charges will flow till the potential difference between these two plates become equal to the potential difference between these two plates. Meaning, this plate and this plate are going to be at the same potential. Similarly, this plate and this plate will be at the same potential. So no more charge flow will be there. Or I can say that the potential difference between the plates of individual capacitors become equal. Did you understand this problem?
Yes, yes.
Right. If you have understood this, now we have to go to the second part of the problem. Let's see what's the second part of the problem. Okay, let's go to the second part of the problem. So the second part of the problem is going to be, what is the energy stored in the electric field before and after the switch is closed? Before the switch is closed means there is no closed path. Whatever charge was there on capacitor 1 remains. So there is nothing very difficult there. So before the switch is closed, no charge will flow out of the capacitor C1. So therefore the initial charge is Q0, it remains Q0. Okay. And we know the potential difference is delta V0. Therefore the initial potential difference is half Q0 square by C1, or you can also write it as half C1 into delta V naught square. We know these values. Just substitute. You get the initial energy. Now what is happening? Close the key. Close the key. Once you close the key, I told you charges will flow till the potential difference becomes the same. So this also becomes delta V. This also becomes delta V. Now, what is the final energy? The final energy is going to be energy stored in the first capacitor plus energy stored in the second capacitor. Okay, I've already calculated delta V. So I can just use that equation. I can write half C1 delta V square plus half C2 delta V square. Delta V already calculated. C1 and C2 we know. Substitute, you get 20 microjoules. This is very simple. Now, how many of you have noticed that the initial energy in capacitor C1 is large when compared to the total energy in the two after they are connected? Can you see that? 70.5 microjoule is the energy in C1 before it was connected. But after it is connected, even if I take the sum of the two energies, it is only 20 microjoule. So the question is, where did the energy go? Where did the energy go? Why is the final energy so less? Why is the final energy so less? Anyone? 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 The final energy is less because in the process of flow of energy, there has been a Joule loss. Joule loss means heating effect. The conductor gets heated. The conductor is this one, the wire. It gets heated. There is some resistance in that. So when a current is flowing, there is a resistance. And you know that I square R is the, anyone knows what is I square R? Power loss. Okay, so there is a loss of power, or there is a loss in, that process is called loss in Joule heating. You will feel a heat in the wire. So energy has been lost there. That's why after the distribution process, the total energy is less. Distribution losses, those of you who pay your electricity bill know. At the DISCOM, where they are producing the power, what is happening is the power produced is something, but by the time it gets distributed to your houses, there is a power loss. Similarly, here also, when all the energy is in one capacitor, it is big. But then when it gets distributed between the two, there is a loss of energy in the distribution process. That's why UF is less than UI. Now let's look at another problem. This problem is an isolated conducting sphere. What is the meaning of isolating? Isolated? Isolated means it's a conducting sphere, not connected to anything, not connected to anything. An isolated conducting sphere whose radius is 6.85 centimeter, it's already charged and then isolated, has a charge Q is equal to 1.25 nanocoulomb. Now you have to find out how much energy is stored in the electric field of this capacitor. It's a capacitor. If it's a capacitor, where is the second plate? If it's a capacitor, it's a spherical capacitor, where is the second plate? The second plate is at infinity. Yeah, second plate is at infinity. Okay, so now, and if you remember in the chapter, in this chapter only, we arrived at a formula for the capacitance of a spherical isolated sphere. The formula was C is equal to 4 pi epsilon naught R. 4 pi epsilon naught R. So we will have to use this for doing our problem. Okay. So you know that energy is half Q square by C. I'm going to take this formula because Q is given and C I can get from the geometry. So therefore half Q square divided by C is 4 pi epsilon naught R. Substitute it. Substitute for Q, substitute for R, and you're getting the energy. You're getting the energy. Okay, now the next question is, what is the, okay, now tell me, where is all the charge sitting? This is an isolated conducting sphere. So where is all the charge sitting? Electrostatic on the surface. The charges are all sitting on the surface, therefore inside the electric field is 0. But outside the electric field depends on the distance. Even on the surface, the potential, the electric field depends on the distance from the center. Okay, so you can say that the electric field is, if Q is the charge, the electric field is 1 by 4 pi epsilon naught Q by capital R square, because we are interested in finding out the energy density at the surface of the sphere. Surface of the sphere means small r equal to capital R. Small r equal to capital R. So we are putting 1 by 4 pi epsilon naught Q by capital R square. Use this in the energy density equation. You are asked to find the energy density at that point. So UE equal to half epsilon naught capital E square. I am putting the subscript E because energy is stored in the electric field. To derive that point, we have put energy density with an E. Okay, half epsilon naught E square. So now substitute for E from here. Then you can calculate. And for capital R, you have to use instead of small r, and then get the energy density. Okay, we have completed here. Epsilon naught, 1 by 4 pi epsilon naught Q by R square whole square. Okay, so here I have to write 1 whole square. And if I do the calculation, this is the answer I will get. Now I have asked a question. What is the radius of the sphere? What is the radius of the sphere? Radius of the sphere is 6.85 centimeter. 6.85 centimeter. Always when you do problem, convert into meter and do it. Okay. Now I am asking you a question. What will be the energy density? Even without doing anything, you can answer this question. What will be the energy density at a point inside?
0.
Why?
Because electric field is 0.
Because electric field is 0. What will be the energy density at infinity? Zero. Because electric field at infinity is 0. Where in this problem is the energy density maximum? At which point is the energy density maximum? At which distance is the energy density maximum? Where is the electric field maximum? Where is the electric field? At the surface. So energy density also will be maximum at the surface. So here is a problem which is telling you that energy density, in the case of parallel plate capacitor, energy density was same everywhere because electric field is uniform. But if you take a spherical capacitor, energy density depends on position. That's why I just asked you this question. Okay. Okay. Now from here, let us move to another topic. This is going to be, we have been talking of dielectrics in the previous chapter. Dielectrics are insulators. And we have seen that whenever you take a dielectric and put it in a uniform electric field E0, the dielectric will get polarized and there will be a polarization field opposite in direction to the applied field. Therefore, the net field inside becomes smaller than the applied field. This you have studied in chapter number 29. Okay, so we are going to just use that concept to study this chapter. So this part of the chapter. So what you're going to now do is, you're going to take a capacitor. This is your capacitor. There is nothing inside, only air is there. You're going to charge it. Charge it so that the potential difference becomes delta V and the plate charge becomes Q. It is fully charged. Now what you do is, after it is fully charged, what happens? The battery is still connected. The battery is still connected. The battery is connected. That means the circuit is still there. But now the battery's potential became equal to this potential. Therefore, it is not going to flow any more charges. It's not going to flow any more charges. So it is, charging is completed. And there is a potential difference, delta V. Which means that there is a field between the two plates. The field will be, electric field will be from positive to negative. Positive to negative. You know the expression for the field, it will be sigma by epsilon naught, where sigma is the surface charge density on the plates. What is surface charge density? Charge divided by area. If A is the area of the plate, then Q by A is sigma, or electric field is Q sigma naught by A. Remember, there is nothing in the space between the two plates. Now what you do is, keeping the battery connected, you take a dielectric slab and introduce it into the space. Introduce it between the two plates of the capacitor so that it fills this gap. You keep the battery connected, the plates of the capacitor which is fully charged is there, take a dielectric slab and then introduce it between the two plates so that the gap between the two plates is now full. Okay, now let us see what is the effect. When you do that, so that's the second picture. That's the second picture. When you do that, let's see what happens. When you do that, this is the dielectric slab which you have put to fill the space. When you do that, you're going to see that the potential difference and the field, after all, field is equal to potential difference divided by the distance. Okay, so what happens is, the potential difference and the electric field will be maintained by the battery. It will be maintained by the battery. Why should the battery maintain? I will tell you. What did we just discuss here? Whenever you put a dielectric in an electric field, the polarization field will lower and effective field inside will be less than the applied field E naught. Same thing will happen here also. Here also same thing will happen. The field will no longer remain E. The field will no longer remain E. It will become smaller than E because the dielectric was put and dielectric got polarized. But what is your battery doing? The battery is sitting there and looking at, it is still connected. It is looking at this capacitor and seeing, hey boss, your value has fallen now. So let me pump some more charge. Let me pump some more charge so that your potential difference will again come to that original value. Are you understanding this? The battery is first fully got charged, so battery is now taking rest. But now the minute you put your dielectric slab, the potential difference between the plates became smaller. So the battery wakes up. It's seeing that there is a smaller potential. So what does it do? It further charges by sending some more charges to the plates. It is sending so that the potential difference delta V gets maintained. Or now the charge on the plates is no longer Q. It is going to take a new value Q prime, where Q prime is greater than Q. Q was the initial value, but now more charges are pumped so that the charge is Q prime and Q prime is greater than Q. Now we have to see what is the effect of this. Okay, so before, so now let us see what, because the dielectric is there, let's call the field as E prime. Let's call the field as E prime. So E prime is going to be sigma prime by epsilon. Why are we putting epsilon and not epsilon naught? Epsilon is the dielectric, it is the electrical constant including the medium. Now it is not free space. You have a dielectric. Therefore, it is not epsilon naught. Epsilon naught is for a free space. But because it's a dielectric which is there, you don't put epsilon naught, you will put epsilon, where epsilon is equal to kappa E into epsilon naught. Kappa E is the dielectric constant of the dielectric. And what is it? Sigma prime. Sigma prime is the surface charge density due to the new charge. Therefore, you can write it as Q prime by A. And then Q prime by A and epsilon becomes kappa E into epsilon naught. Okay, and we have seen that this field is going to be the same as the initial field, or E prime will be the same as E. And the expression for E was Q by epsilon naught A, which we wrote in the previous page. Or making a comparison between this and this, we are able to get Q prime in terms of Q. Q prime in terms of Q. You're seeing that Q prime is equal to kappa into Q. Q prime is equal to kappa into Q. So the dielectric constant kappa decides how much extra charge went onto the plate. And by now you must have understood that more charge means more energy. Okay, or if you want to know what is the extra charge that went, that is the difference between the final charge and the initial charge. So you can see that this is the expression. Okay, now let us see what is the effect of this dielectric slab on the capacitance. Let the new capacitance value be C prime. C prime will be charge divided by delta V. Charge is Q prime, which is kappa E into Q. Or you're seeing that the capacitance value, because you put a dielectric inside, the capacitance value increased. The capacitance value increased by a factor kappa E. And if you want to now write the formula for C prime will be epsilon A by D, not epsilon naught A by D, it is epsilon A by D, which is equal to kappa E into epsilon naught A by D, which is equal to kappa E into C. Okay? Or in other words, the capacitance value increased by a factor kappa E when you put in a dielectric. Now let us see what is the effect on energy. Let the new energy be U prime. U prime is half C prime delta V square. Delta V is maintained, so delta V square. And you know C prime is kappa into C. Or you are able to see that the new energy is kappa E times the initial energy. Or you're finding that the energy also increased by a factor kappa E. So what is the effect of introducing a dielectric slab keeping the battery connected? The effect of introducing a dielectric slab enhances the performance of the capacitor. It increases the charge on the capacitor using the same battery. It increases the charge on the plates. It increases the capacitance value. Therefore, it increases the energy stored. Okay? So that's the reason why you use dielectrics in a capacitor. Now, how did we do this entire process? We connected a battery, charged the capacitor, kept the battery as it is, and then introduced the dielectric. Next, what we'll do is, we will connect a battery, charge a capacitor. Okay, after charging, we'll remove the battery. We'll remove the battery and then put in a dielectric and see how different that is going to be from this. Right. So what is this? It is filling a capacitor with a dielectric after disconnecting the battery. So look at this picture. You've charged it to potential delta V plus Q minus Q is a charge on the plates. It is empty initially. Now you remove the battery. Once you remove the battery, what do you think will be a constant? Q, V, C. Which do you think will remain a constant? C will remain a constant because it is geometry. What about Q? Q also will remain a constant because it doesn't have any place to go. The circuit is open, so charge cannot move out of the plates. Therefore, Q remains constant. Okay? Now, whereas in the previous problem, what happened? Delta V was maintained a constant, Q increased. Whereas here, Q is going to remain a constant. So before that, let us, as usual, write the expression for the initial electric field. It is Q by epsilon naught A. Now, disconnect the battery, introduce the slab so that the gap is fully filled. The charge Q, this is the important step. The charge Q on the plates is maintained. Charge Q on the plate is maintained. Okay? After you have introduced the plate, the dielectric slab. And you know that the job of a dielectric is to reduce the electric field or reduce the potential difference. Therefore, the potential difference now becomes delta V prime, different from delta V. Now, the battery is not there, so it is not able to help in any way by introducing more charges. So, the potential difference and the field are going to be delta V is going to be, delta V prime is going to be less than delta V, the initial potential difference. Similarly, the new field is also going to be less than the initial field. So let us try to get the expression for the new field. New field is Q by epsilon A, not epsilon naught A, it is epsilon A. Epsilon is kappa E into epsilon naught. Therefore, you are able to see that it is E by kappa E. That means the electric field reduced by a factor kappa E. It is not multiplying, it is dividing by kappa E. Electric field fell, which means potential difference also falls. Here I should have put a, there is something missing there. Here I should put a prime. So delta V prime equal to kappa E into delta V. So now let us see the effect of this on the capacitance value. Let the new capacitance value be C prime. C prime is Q by, Q is a constant. So Q by delta V prime. Delta V prime. And delta V prime is delta V by kappa E. Kappa E goes to the numerator. So you're able to see that the capacitance, new capacitance is kappa E into C, or the value of the capacitance again increased. When you put in a dielectric, the capacitance value increased by a factor kappa E. But what is the difference between the previous page and this one? There what happened? E and delta V remained the same. Q prime was greater than Q. C prime was greater than C. Here what is happening? Q is a constant. Delta V and E decreased. Potential difference in electric field decreased, but capacitance again increased. Now let us see what happens to the energy. So we are able to right now conclude that the capacitance value increased by a factor kappa E, just as in the previous case. So you conclude that the capacitance value of any capacitor will increase by a factor kappa E and does not depend on whether you're going to pull out the battery first or you're going to insert keeping the battery. It doesn't matter. Okay, so that's one thing that you're seeing. Now let us come to energy. Let's come to energy. The final energy is half C square by Q square by C prime. I'm not going to use that C prime delta V prime square because delta V changed. So let's not do that. Always try to use the formula where a factor is not changing. So Q is not changing. So let's use the formula half Q square by C prime. Half Q square by C prime. After looking at this, can you tell me what happens to the energy stored? Will it increase or decrease? Will the energy stored increase or decrease? What is the initial energy? Half Q square by C. Final energy is half Q square by C prime. Denominator is greater in the second case. Therefore, energy decreased. Okay? Please expect these questions in the examination. Okay, now let us have a picture of the capacitor. So these are your capacitors. Initially, there is nothing. You have charged it. Plus Q, minus Q. Electric field is E naught at some point here from the positive to negative plate. Now, we are interested in finding an expression for E naught. Finding an expression for E naught. We can find an expression for E naught by using Gauss law. What we'll do is, we will consider a Gaussian surface as a cuboid Gaussian surface enclosing the charges on one plate. Enclosing the charges on one plate. And what is the charge? The charge is plus Q. Okay, and here for this surface, electric field is 0. Because it is inside the conductor, electric field is 0. And for this surface, the electric field is E naught. Okay, and our dA vector is this. Okay, so now if I do integral E dot dA, I will only have to consider this area. I'm showing a line, but this is actually a area. I have to just take only this area. So it is E naught into A. And what is on the right hand side? Net charge divided by epsilon naught. That is Q by epsilon naught. Or you're getting your E naught as Q by epsilon naught A. And this charge Q is called the free charge. Q is called the free charge. Free charge means charges which are able to move. They are on the metal surface. That's why it's called the free charge. Okay? Or this charge happened because of actual movement of charges. Charges from the battery, through the battery. Now let us introduce the dielectric. The dielectric is introduced after disconnecting the battery. If you disconnect the battery, charge remains a constant. Okay? And what will happen to the slab? The slab will get polarized. The dielectric slab will get polarized. There will be, look at this, there will be a minus Q prime charge on the place Please guys, remember Q prime in the previous pages was used to talk about the final charge on the capacitor plate. The author has done that mistake, not me. Q prime is a symbol used for the charges on the plate after dielectric was introduced. Whereas here in this page, Q prime is the polarization charge on the surface of the dielectric. Okay, so you can see that a negative charge will get introduced on the positive side and positive charge will get introduced on the negative side. This comes from polarization. Go to chapter number 29. Okay, now as a result, what will happen is there will be a polarization charge from negative plate to the positive plate. Applied field is from positive plate to the negative plate. Therefore, the net field inside is now just E. It is not E naught, it is just E and it is less than E naught. It is E and less than E naught. So now let us apply Gauss law. Okay, when you apply Gauss law now, the net charge inside the Gaussian surface is Q minus Q prime. One free charge is Q. Q prime is the polarization charge. It is negative. Therefore, Q minus Q prime. And on the left-hand side, you see, it is integral E dot dA. It is E into A because this surface is going to have a field E and area is A. So you get E into A is Q minus Q prime by epsilon naught. Notice here, I have written epsilon naught and not epsilon. I've written epsilon naught and not epsilon. That is because the presence of the dielectric is accounted for by taking these polarization charges minus Q prime and plus Q prime. Okay, the presence of the dielectric is accounted for by taking the polarization charge minus Q prime and plus Q prime. So you don't have to write epsilon, you can write it as epsilon naught. Okay. Therefore, the electric field will now become, you can just finish it. You'll see it is Q minus Q prime by A epsilon naught. Q prime is called induced charge. It is also called polarization charge. It's called induced charge or polarization charge. Okay. So that's how you calculate the electric field. Now, there is also another formula for the same E, which we have used in the previous discussion. Electric field, net electric field inside the material can also be written as Q by A epsilon. Q by A epsilon. Here what we are doing is, the presence of the dielectric is taken in the form of the property of the material. The property of the material, and we are not taking the polarization charge. We are only considering the free charge. Okay? Or whenever you're writing Gauss law for these kind of situations, you have to remember one thing. You can write Gauss law like this. Here what are we doing? Integral E dot dA is Q by epsilon. Here the permittivity of the medium is taken and we are not considering Q prime, the polarization charge. Okay? Look at the next way of writing. Integral E dot dA is Q minus Q prime by epsilon naught. The presence of the dielectric is now written in the form of induced charge, not in terms of permittivity. In the first case, what happens is, you can treat it as if there is one capacitor and there is another capacitor sitting inside and it's free space inside. That is, you're going to not take the dielectric in terms of epsilon, you're going to take it in terms of the polarization charge. Another way is, you have only the parent charges, the free charges, but then the material inside is epsilon. So that is another way of writing. Don't do both simultaneously. The presence of the dielectric should be reflected only in one of the ways, either as epsilon or in the form of Q prime, which is the polarization charge. Okay, with this we are actually finishing off the chapter. Okay, I think I'll take 2 minutes and just take you through this problem. You have a parallel plate capacitor. Capacitance value is 13.5 picofarad with a potential difference of 12.5 volts between the plates. The charging battery is now disconnected and a porcelain slab is slipped between the plates. What is the stored energy of the unit both before and after the slab is introduced? Before the slab is introduced, there is no problem at all. I know the capacitance value, I know the potential difference. Just use it, get the energy. Now, after the slab is introduced, let us see how to get the energy. Now, how are you doing it? You're disconnecting the battery and then doing it. That's what the problem says. After the battery is removed, circuit is open, charge on the plates will remain a constant. Now, when the dielectric slab is introduced, electric field and potential difference will decrease. And the new value of potential difference will be delta V prime equal to delta V by kappa E. We just saw. And the capacitance value increases by a factor kappa E. Therefore, the new energy can be written as half C naught square, C naught prime delta V prime square. Delta V prime square. Okay, so just substitute. C naught prime is kappa E C naught and delta V prime is delta V by kappa E. Or in other words, you're finding that the energy is 162 picojoule. That's what we saw some minutes back also. If the battery is removed and you put in a dielectric slab, energy decreases. Energy decreases. Okay, and you look at this. The same problem can be done in another fashion also. You can actually use this formula. UF is equal to half Q square by C naught prime. Using that method also, you will get the same answer. Now the question is, where did the energy go? Where did the energy go? Without capacity, without dielectric, you had more energy. When you put the dielectric, energy is lost. Where did the energy go? So you can actually answer that question by saying that when you try to push the dielectric inside, this capacitance will not allow. It doesn't like the electric field or the potential difference to reduce. So it will actually push against the dielectric. It will push against the dielectric. But an external agent is doing work and then doing the job of pushing it in. So in that process, the capacitor is losing energy. Finally, there is also one last problem. This is just a part of that problem only. Calculate the electric field in the dielectric slab. Electric field is E. Okay, just now we have seen how the electric field will change. You can write E is equal to E naught by kappa E. Electric field is reducing. Next, what is the potential difference? And please, in this problem, he is not going to put a dielectric slab of width of thickness D. D is the gap between the plates. He is not putting a dielectric slab D of thickness D. He is going to put a dielectric slab of thickness B. He is putting a dielectric slab of thickness B. B is less than D. Okay. Now, after putting the slab, the electric field is going to become less. How will you calculate that electric field? How will you calculate that electric field? So for doing that, you have to use this expression, the relationship between potential difference and electric field. Okay? And you have to look at this as three different regions. Region 1, region 2, region 3. In region 1, the electric field remains E naught because there is no dielectric there. In region 3 also, the electric field will be E naught only. Only in region 2, the electric field will be E because there is dielectric there. So you can divide this integral into three parts. 1, 2, 3. Okay. Therefore, for part 1 and 3 together, the value will be E naught into this distance plus E naught into this distance. So what will this be? This will be total minus the length taken by the dielectric. Therefore, it will be D minus B. That's how you get this. Now, what is the electric field because of the dielectric? That is E. Okay, therefore, the thickness is B, so EB. Now substitute all this. you will get the potential difference between the plates. If instead of this dielectric, if the dielectric slab had a thickness D, if the dielectric slab had a thickness D, then you don't have to write it into three parts like that. Straight away, you would have written E into D equal to delta V prime. Okay? Then next, what is the capacitance? Is the next question. Capacitance is charge divided by potential difference. Charge is a constant, put that. Potential difference is this. You get the new capacitance. Similarly, you can also find what is a polarization field. Polarization field also you can find out if you are interested. You can try that yourself. Okay, so I wanted to save time. That's the reason why I wrote it and then came to class. Please go through these things completely. All the steps are put there. Please go through. And if you have any doubts, you can always get back to me. But only thing, I have a request. Try to keep your doubts till 5:30 in the evening. And then from 8 to 10. Because between that time, what happens is now no maids, nothing. We are our maids, we are our cooks, we have to do everything. Okay. So up to 5:30 you can call. You can ask me doubts. Similarly, you can also do it after 8 to 10. And I would prefer if you don't send private messages, you can put it in the WhatsApp group. That way everybody will see the doubt. No doubt is silly, no doubt is stupid. No doubt is silly, no doubt is stupid. If you put it there, your friends will also participate in the discussion. Okay, so I finished this chapter. So now you can actually prepare for the test. Next class, I'll start with a new chapter. So you guys can actually leave, stop recording.